Raven Engineering 2-plane horizontal dynamic crankshaft balancing machine, model BH-50 with semi-automatic drill correction. The operator will begin the audit cycle by pressing the start cycle and common push buttons simultaneously. Displayed here is a typical audit cycle. The part speed and transducer signal stability are monitored. Upon completion of the audit cycle, the correction screen is displayed. This screen indicates to the operator how many holes are to be drilled as well as angular locations. But before further information regarding the correction process, it is necessary to explain the part setup procedure. The HBI-25 indication system has 3 modes of operation. The first mode seen was the run mode, which is the production mode. The second is the calibration mode, and the third is the part setup mode. This mode or screen is used to input part dimensional, calibration, and correction information. In the setup mode, the first parameter is the part ID number. A standard machine has 120 part ID code configurations. We provide an option to extend this to 2040 part ID configurations. Each parameter box is highlighted for the operator. Also located at the bottom of the screen is a description box to prompt the desired information from the operator. Next is the motor stop option that determines how many samples per audit are taken. Currently it is set to auto 5 for 5 readings. Method of correction. Set this to light to add mass to balance the part, or heavy 1 for axial, or heavy 2 for radial correction to remove mass. Nulling, which is tooling compensation, can be turned on or off. In the center section of the screen contains part dimensional information, such as the type of units used, inches or millimeters, the number of decimal places to be displayed during the audit ranging from 1 to 5, referring to the diagram above. The L dimension is the distance from the left support to the left correction plane. The W dimension is the distance between the left and right correction planes. The S dimension is from the left support to the right support. The R1 dimension is the left correction calibration radius. The R2 dimension is the right correction calibration radius. The R3 dimension is the center correction calibration radius, used for inline crankshafts. Going to the upper right hand side is the calibration information. First is the unit of measure of the mass in ounces or grams. Next, located here, is a left plane and right plane value for the calibration mass. Below this is the left and right plane angular location of the mass. This information provides a known mass at a known angle. In the Units box, various units of balance measure or raw weight can be selected. For example, ounce inches, gram centimeters, or grams. The rate parameter determines how many samples per revolution are taken. The QC limit is the part balance tolerance for left and right planes. Below this is the minimum and maximum RPM values for accepting readings. Starting angle and ending angle refer to the angular values for the crankshaft counterweights for inline crankshafts. For all other parts, these should be set at 0 degrees and 0 degrees. Tooling diameter. There are 4 different drill sizes available to the user. By pressing the next key, the next tooling diameter can be keyed in. Pitch angle is the angular distance between correction holes, center to center. The density parameter contains the specific density of the material to be corrected. Maximum depth of correction hole. Tip angle of the drills used for correction. Calibration RPM displays the speed setting of the previous calibration. Lastly is part name. Here alphanumeric, numeric, or a combination of both types of data for the part description can be input. Pressing the F2 key switches from setup mode to calibration mode. There are 4 steps to calibrating the machine in calibration mode. First, the operator places the bob weights on the crankshaft calibration master gauge. Our experienced staff can help in the design and manufacture of these weights. Step 1 is indicated on screen as Cal 1. We begin by starting an audit cycle with no calibration weight installed. As the part comes up to speed, the RPM box turns from red to green. In the signal stability box, when the signal becomes stable, it also turns green. When both boxes are green, the audit can be ended by the operator. This step provided the machine with an electronic zero baseline. The HBI-25 automatically advances to Cal Step 2 when the part comes to rest. At each Cal step, the operator can reset to repeat the previous step. In Cal Step 2, the indication box at the bottom of the screen directs the operator to attach a 24.28 gram weight on the master gauge at an angle of 93.9 degrees. The operator presses the start and comment push buttons to begin another audit cycle. When the 2 conditions of rotational speed and signal stability are met, the audit is stopped. Advancing to Cal Step 3, the weight is transferred to the right plane and the audit process is repeated. Using known amounts of mass at known angles provides the machine with an accurate means of scaling the transducer input. At the end of the 3rd audit, the weight is removed for Cal Step 4. This last step is provided for determining the tooling compensation offset. It is effective only on end-drive systems. The part is uncoupled and rotated 180 degrees and recoupled. Then the last audit is performed. Here a belt drive system is used, which makes this step mute. After the audit is complete, the operator is prompted to save the calibration. Pressing the F1 key places the HBI-25 into run mode, where an audit of the master gauge indicates the accuracy of the calibration process. Typical production cycle is as follows. After loading a production part with the bob weights, if required, into the cradle and coupling the part via end drive or belt drive, the initial audit is started. The audit is automatically stopped by the indication system. Upon completion of the audit, the correction information is indicated on the screen. Shown here is one hole of correction on the left plane. The first column is the hole number. The second is the amount of mass in grams to be removed. The third column is the depth of the hole. The operator indexes the part to the prescribed angle and the brake is automatically applied. The part lift is actuated, which raises the part above the rollers, thus protecting them. The operator then slides the drill into position on the left plane. This can also be automated. The air feed is actuated to begin the automatic drill process. When the drill touches the part surface, it is indicated to the HVI-25 via a torque monitor, and the HVI-25 then controls the depth of the hole. Hole depth is indicated in real time at the bottom of the correction screen. After making a correction on both left and right planes, the part is re-audited. The green accept boxes on the left and right sides indicate that the part is within tolerance on both planes. At the end of the audit cycle, it is possible to log data to a standard parallel printer or to a floppy drive. This balancer is a non-standard model due to having both an in-drive and belt drive system. The machine cradle's rugged construction can be designed to turn the part on either rollers or V-pads. Adjustable pulleys on the belt drive allow for a variety of part sizes. The supports are mounted on ways and are adjustable for varying part lengths. The chip evacuation system is made up of 4 components. 1. The vacuum block. 2. Quick disconnect drill holder with a rotary coolant coupling. 3. Easily removable lower vacuum drill bushing. 4. Spring-loaded slides. This system is connected to a standard Clausing 20-inch drill. The guard moves out of the way easily for drill maintenance. The automatic drill depth control requires an encoder assembly using a simple rack and pinion system. For manual correction, a digital scale is integrated into the air feed system. During correction, the operator can select the left, center, or right plane. The 4-position selector switch selects between 4 possible drill sizes. The air over oil air feed is controlled by 2 pneumatic push buttons. The drill holders can be quickly removed for insert replacement during production. At the rear of the machine, components and pneumatic controls are mounted. The AccuLube system is provided to extend drill tool life and to reduce the stress on the parts. The load sentinel is a torque monitor that is used to indicate the drill touch point on the part. CKD pneumatic controls are standard. We can build to the customer request. A separate pneumatic system is used for the chip evacuation system, providing machine flexibility. front of the control cabinet contains the motion control devices. Located in the rear of the cabinet is the HBI-25 indication computer, as well as support components. Standard machines use 24-volt DC relay logic controls. PLC controls are available upon request. Each machine is supplied with a complete operational manual that contains all the information on the setup, calibration, and production processes, and comes in a simple, user-friendly format. Additionally, our maintenance procedures, OEM component manuals, and full electric, pneumatic, and assembly schematics. Each section is tabbed for quick reference. At Raven Engineering, we create a complete balancing solution that meets or exceeds our customers' needs. Thanks from all of us at Raven Engineering.